All right, let's pick up where we left off on the last one. We were talking about sequences. Let's take a look at a couple of other types of sequences and a couple of examples that we should view. Let's take a look at this sequence. I've got a sequence of e to the n over n to the eighth, and I'm going to look at this sequence from n equals 1 to infinity. And again, I'd like to find out some information about how this thing behaves. Does it converge? Does it diverge? If it converges, what does it converge to? Well, I mean, technically we could L'Hopital this 8 times, right? We can't really divide numerator and denominator by a polynomial because we've already divided by n to the eighth. What do? Yeah, you could L'Hopital it 8 times, but what if you L'Hopital it 8 times? You realize that at the end, you would end up with some form of a constant on the bottom, but you would still end up with an e to the n on top, right? E to the n derives itself as e to the n 8 times. On the bottom, essentially, you would end up with 8 factorial, right? 8 times 7 times 6, and so forth. Apply the limit as n goes to infinity, and this thing approaches infinity, right? It diverges. So you can skip a little bit of that work of showing every single step if you show something that lets me believe that you understand what's happening here. You don't actually have to show 8 L'Hopital rules all the way along, because you can see that the top is going to grow much faster than the bottom. What if you had a case like this? What if you had an a sub n equals 4n to the 10th plus 8n to the 5th plus 2 over 7n to the 10th plus, I don't know, 1,000, right? And I want to find out whether this converges or diverges as a sequence. Yeah, again, I could L'Hopital this thing 10 times, but what if I divide numerator and denominator by 10, right? Divide numerator and denominator by n to the 10th, and I'll end up with a 4 plus an 8 over n to the 5th, plus a 2 over n to the 10th, and on the bottom, a 7 plus 1,000 over n to the 10th. All right. This and that are all going to go to 0, because as the denominator gets bigger and bigger, the numerator stays a constant, it becomes 0. So this thing actually approaches 4/7. This thing converges. And that's one of the reasons that you would want to run some type of test on this thing, is because, yeah, you could see that the terms are decreasing, but you would have to put an awful lot of n values in there before you saw that this thing was heading to exactly 4/7, if you ever saw that, right? These things are not the easiest things to see by eyeballing. So yeah, you can see if it approaches 0, you can see if it approaches infinity, but you should also run these tests so that you can see what happens if it begins to approach a constant value. All right, let's try one more of these, and then we'll talk a little bit about types of sequences. All right, suppose I gave you this. I want to find for a sub n equals 1 plus 2 over n to the n. And I want to start this thing at 1 and go up to infinity. Now, here's my warning. Ooh, I should write the warning in red. Warning. 1 to the infinity is not 1. So you might say, all right, I'm going to take the limit as n goes to infinity. This 2 to the n piece here gets very small, so I'll get 1 to the infinity, and my answer is 1, and I'm done. Except that it's not. So, if 1 to the infinity is not 1, then what is it? Well, let's apply a limit, right? Let's call it y. Y will be the limit as n approaches infinity of 1 plus 2 over n to the n. Well, it would make sense to me to take natural logs of both sides so that I can then drop down this exponent, and when you drop the exponent, it moves in front of the log. So now on the left side, I've got the natural log of y. On the right-hand side, I've got n times the natural log of 1 plus 2 over n, and I'm going to apply to that the limit as n approaches infinity. All right, well, what kind of case is this? This is a case of infinity times 0, right? Because as n approaches infinity, you'll get infinity. As the natural log approaches, as the n down the bottom approaches infinity, you get the natural log of 1. Natural log of 1 is 0. So this is a case of infinity times 0. It's kind of L'Hopital-ish, but it's not actually able to be done by L'Hopital's rule unless we sort of change perspectives. So I'd like to rewrite this as a limit as n approaches infinity. Let's leave the natural log of 1 plus 2 over n on the top. And on the bottom, I'm going to write the denominator as 1 over n. So instead of putting this n on the top, I'm going to write it as a 1 over n on the bottom. Okay. So now what does this leave me with? On the top, the natural log of 1 is 0. 1 over quote-unquote infinity is also 0. I got a case of 0 over 0. Now I can L'Hopital. All right, just kind of follow the bouncing ball in this one because we've got to take a derivative of something that's already in fraction form. So in the numerator, when I take the derivative of that natural log, I get 1 over 1 plus 2 over n, right? 1 over u. But don't forget, times the derivative of the inside. So the derivative of the inside is going to be the derivative of 2 over n. Well, here, I'll come over on the side a little bit. How do I derive 2 over n? That means I'm deriving 2n to the negative first, which is negative 2n to the negative second, which is negative 2 over n squared. So this thing here is going to be multiplied by negative 2 over n squared. On the bottom, we also have to derive the bottom, right? That's how we L'Hopital. If I derive a 1 over n, I end up with a negative 1 over n squared. And to all of this, I'm applying the limit as n approaches infinity. All right, what's the good news here? Look at your negative 2 divided by n squared, and you got a negative 1 divided by n squared. Those two things simply become a 2. Right? So I end up with a 2 There we go, a 2 over 1 plus 2 over n. When I apply the limit as n approaches infinity, that gives me 2. Great, but the problem's not over yet because we've lost the left side of our equation. So here, we'll scroll up a little bit. Remember that originally we had a natural log of y on the left side. Natural log of y on the left side, a 2 on the right side, and now we're almost done. E to both sides, and you begin to realize that what I have is actually e squared. So this thing is the limit. So that limit is finite. Because I have a finite limit, that sequence converges. And that sequence converges to e squared. And again, I don't know that I would have seen that if I had just written out the first 300 to 400 terms. Hey, we're going to be home for a while, so let's write out the first 400 terms of this. Will I have seen in decimal form that gets close to e squared? Probably not. So again, it's important to calculate these limits. All right, let's talk about types of sequences. All right, so types of sequences. The first type I'm going to look at is a sequence that is non-decreasing. And a non-decreasing sequence is simply the case where the n plus first term is greater than or equal to the nth term. And that's why it's called non-decreasing. So for example, if I wrote out the sequence 2, 3, 4, ... does that meet the criteria? 4 is bigger than 3. 3 is bigger than 2. If I went to the next term, 5 is bigger than 4. So it is non-decreasing. Every term is at least the same as the term before it. So that's why it's not called increasing, because of that equality bit, right? Technically, the sequence 3, 3, 3, and so forth is non-decreasing, and it's kind of boring, but it is non-decreasing. All right, what do you think the next one's going to be? I know, I'm talking to a video machine, but hey, you may be answering on your end. So instead of non-decreasing, how about a non-increasing sequence? And as you might guess, a non-increasing sequence is going to be the same thing above it, except flip the sign around. So a sub n plus 1 is less than or equal to a sub n. So if I had something like, let's say, 1 plus 1 over n. Okay, let's take a look at that sequence. The first term is going to be 2. The next term is going to be 1 plus a half, which is 1 and a half, so 3 halves. The next one is going to be 4 thirds. The next one then will be 5 fourths. and this thing continues. If you'd rather see it as mixed numbers, then you've got 2, you've got 1.5, you've got 1 1/3, you got 1 1/4, and so forth. So this thing is certainly not getting bigger. It appears that it's getting smaller. But again, we don't call it decreasing because non-increasing, again, allows for that possibility that that sequence of 3s is also non-increasing. So we say non-decreasing and non-increasing as opposed to strictly increasing and decreasing. All right, there's something else that's true about both of these. I'm going to slide this up just enough that I can write one more thing underneath it. And that is the term monotonic. Okay? A sequence that is monotonic goes only in one direction. So now I can begin to apply a second term to those terms that are already there. So for example, my sequence can be monotonic and non-decreasing. And that's what this sequence over here is, right? It's monotonic and non-decreasing. It's going only in one direction, and the terms are not getting smaller. The terms are actually getting bigger, right? So the same thing is actually true of this guy down here, right? He's monotonic and non-increasing because his terms are going in only one direction. They're not leveling off at some point. All right, we could have gone back to, in fact, we can. We can go back to this sequence over here and begin to look at the terms of 1 plus 2 over n to the n. And if we wrote out those terms, we would actually find out that that is also monotonic. So if I wrote out the terms, I threw it on a table of values, and I got a 3, a 4, a 4.6, a 5.1, a 5.4, and so forth. So this eventually will begin to approach e squared. I actually don't know what the decimal approximation for e squared is, but eventually it will begin to approach that, but only going in one direction, right? Not approaching from two directions. All right, let's take a look at two other cases here. All right. If I scroll my blackboard down, I can't do this on a whiteboard, can I? All right, let's try this. Suppose I look at this sort of frightening looking sequence. I've got a -1 to the n cubed over n cubed plus 1. And I'd like to take a look at this sequence and write out a number of terms. First of all, I can tell the sequence is going to alternate, right? That's what that -1 to the n does. It tells me the sequence is going to alternate. But what are the terms going to be? So what I did is I threw this on Desmos. Right, so if you look at the left side over here, just to make life a little bit easier for myself, I actually put the same set of terms in there twice. So these are the first 5 terms. And then, here, if I slide this over, yeah, there you go. So if I look at these are the first 5 terms, and these are the next 5 terms. So it's alternating. It's -1/2, it's about +0.9. It's -0.96, it's +0.98. -0.99, and so forth, and it seems like it's getting real close to 1 real quickly. All right, so slide over here and take a look at what Desmos graphed me. That's the first term, that's the second term, that's the third term, that's the fourth term, fifth term, and so forth. So if you notice what's happening, it's not getting wildly different from each other, right? It's not going up like we had that -2 to the n in the previous video that just kept going up further and further, 2, 4, 8, 16, 32, and so forth. This thing's not doing anything wild, but if I said, so what value does this approach? You could look at just the top half here and you go, oh, it looks like it's heading towards 1, right? There's about a 0.9, a 0.96, a 0.99. This looks like it's getting to 1 real fast. Down the bottom, if you looked at this, you'd say it's going to -1. Well, there's no limit unless we agree on both sides. So if you say 1 and I say -1, it doesn't count unless we agree. So this sequence here actually diverges because the positive terms go towards 1, so the positive terms approach 1, but the negative terms approach -1. Well, clearly those two things are not equal, so we say that this sequence diverges because it does not produce a limit. And it doesn't produce a limit by doing something like going to infinity or negative infinity. It just doesn't produce a limit by not agreeing where those terms are heading. If I were to remove that -1 to the n, by the way, then that thing would converge. It would converge to 1 because both sides would approach the same value. All right, let's look at one more. Let's look at this. This is going to look a little bit similar to something we did before, but not quite the same. This is a cosine of n over n. So I could start writing out the first few terms, but that would be weird because remember I'm operating in radians. I don't know what the cosine of 1 radian is off the top of my head. I don't know what the cosine of 2 radians is off the top of my head. I don't know what the cosine of 3 radians is off the top of my head. So how do I compensate for that? How do I figure out what that limit is? Because it either has a limit or it doesn't. What can I do? Let's go back and bring back the squeeze theorem, or the sandwich theorem as I've called it before. We know something about the cosine of n, right? We know that the cosine of n cannot be more than 1, and it cannot be less than -1, right? That's a fact. Now, let's divide everything through by n. So I'm going to divide this by n. I'm going to divide that by n. I'm going to divide that by n. And then I'm going to take limits of everything. So I want to find out what is the limit as n approaches infinity of the first piece. I'd like to know the limit as n approaches infinity of the middle term. And I'd like to find out what is the limit as n approaches infinity of the third term. Well, the first and the last ones are easy, right? This first guy gives me a 0. This thing over here in the end gives me a 0. Well, what I'm trying to find is what's on the inside here, right? That limit as n approaches infinity of the cosine of n over n. Well, if both of the outside pieces are 0, then the limit must be 0. So I can say that this thing converges and the limit is 0. Which would make sense when you think about it, right? If that cosine of n is never going to be bigger than 1 or less than -1, then as those n values in the denominator get more and more, then the whole thing just begins to approach 0. All right, so let's take a look at one or two definitions here. So suppose I have a sequence that is both monotonic and bounded. Right? So suppose I have a sequence that is monotonic and bounded. You saw a couple of examples of bounded sequences before where the limit approaches some constant. So we had one that approached 4/7. We had one that approached e squared. Well, what does it look like if it's monotonically increasing and bounded? Maybe the terms begin to look like this, and there's some bound up here. If it's monotonic and bounded, then it converges. Right? It has to. If it's bounded by some value, always increasing, and approaches that value, then it converges. I bet you it works the other way too. What if I have something that is monotonically decreasing and is bounded? Well, again, if monotonically decreasing and bounded, that sequence converges. Okay. The only other thing that comes up in this section is something we call relative rates of growth. So let's take a minute and talk about relative rates of growth. And we're not talking about actual relatives, like whether you're growing faster than your cousin or something like that. These are relative rates of growth between functions. So suppose I had 3 functions. I've got y equals x, I got y equals 2x, and I got y equals e to the x. And I'd like to figure out which of these grow the fastest. Well, here's my rule. If I take the limit as n approaches infinity of one set of values over the other, right? One sequence of values over the other, and I get infinity, then a sub n grows faster. Okay, so if I compare the two, take the limit of one over the other, if I get infinity, then the top one grows faster. What do you think happens if I take the limit as n approaches infinity of a sub n over b sub n, and I get 0? Well, now the bottom one is growing faster. One thing that you get out of this is that it doesn't matter which function you put on top and which function you put on the bottom. it just flips them around. So if you get infinity, that means the top one grows faster. If you get 0, that means the bottom one grows faster. Well, there is a third option, and that is, what if they grow at the same rate? So if you take the limit as n approaches infinity of a sub n over b sub n, and you get some finite value, then they grow at the same rate. And that leads to perhaps some surprising results. So let's take a look at the functions that I had before. So if I compare e to the x to 2x, let's say. So I'll take the limit as n approaches infinity of e to the x over 2x. All right, this is a case of infinity over infinity. So we L'Hopital, and we get e to the x over 2, right? Applying the limit, well, that shouldn't be an n, that should be an x. Or I have to change everything and make amends. Right? Take the limit as x approaches infinity, and I get infinity. So what does that mean? That means that this thing grows faster. So e to the x grows faster. You realize if I had flipped the fraction over here and put the e to the x on the bottom, I would get 2 over e to the x, which would be 0, and e to the x would still grow faster. So what if I wanted to compare, let's say, y equals x to y equals 10x, and I want to figure out which of these grows faster? Well, you might look at it and go, well, clearly 10x grows faster, right? It's 10 times as big. Let's find out. Let's take the limit as x approaches infinity of 10x over x. I get 10. That's a constant. So those two functions actually grow at the same rate. Now, how is it possible to grow at the same rate? Doesn't one grow faster than the other? Well, think of it as zooming way out in your mind, right? If you're graphing on a window from like negative 20 to 20, 10x is going to take off a whole lot faster than x. But now zoom out to like, negative 70 trillion to 70 trillion. Compare something like x 10x and e to the x, or x 10x and x factorial. Well, those e to the x's and x factorials are going to grow a whole lot faster than either x or 10 to the x or 20 to the x or 100 to the x. In other words, exponential outstrips linear. So x and 10 to the x are both linear. They'll grow at the same rate. Ooh, let's try one more. Let's compare n to the n to n factorial to see which one grows faster. So you might say, all right, well, I know how to do this. I'm going to take the limit as n approaches infinity of n to the n over n factorial. Well, great. That's a case of infinity over infinity. How do you derive either one of them? I mean, I suppose the top we could use logarithmic differentiation for, but how do you derive n factorial? Well, in this case, what we're going to do is we're just going to kind of look at what that means. N to the n means n times n times n, n times. On the bottom, n factorial means n times n minus 1 times n minus 2 until I get down to 1. So it looks like these factors are going to be larger. All right, so on the bottom, I mean, the first terms are obviously the same, but on the bottom, you're going to start getting smaller and smaller terms, and the top will outstrip the bottom. So n to the n grows faster. All right, and that's the end of 10-1 and 10-2 on sequences.